Hello students, welcome back to our course Environmental Modeling and Simulation. Today we are going to continue our discussion on bifurcations in 2D systems. The example we used in the previous lecture was the example of autocatalytic protein expression, and we were looking at how the levels of mRNA and the protein change. We used a very simple model. We drew the phase portrait using null clines, and now what we are going to do is figure out how the trajectories behave around the intersection points of null cline. So this is our model. This is a non-dimensionalized model. Remember that. The x represents is not exactly equal to, but it represents the level of protein. And the y represents the level of mRNA. The phase portrait that we drew, so let's say x is here, the y is here. We have a straight line, which is the x null cline. It's given by the very simple equation y is equal to ax. And the y null cline, which is given by this equation here, y is equal to 1 by b x squared by 1 plus x squared, is a sigmoidal curve as we saw. So given a certain value of a, if a is small enough, this is a y null cline. If a is small enough, we'll have 3 fixed points. So we have one fixed point here, one here, and one fixed point here. And now we want to understand the flow of trajectories around this fixed point to get a better impression of the phase portrait that we are trying to draw here. Okay, so the approach here is to look at the signs of dx by dt in the various regions that are demarcated by these two null clines. So let's start with the top big region. So we are going to start with this region. Which is above both the null clines. So in this region, the y is more than it should be for both dx by dt to be equal to 0, because it is above both the null clines. And we notice that when y is bigger than it needs to be for dx by dt to be equal to 0, which is the yellow area, then dx by dt will be positive. So what we have is the rate at which x is changing with time is positive. Now in the dy by dt, when y is more than it needs to be for dy by dt to be 0, what we notice is that dy by dt becomes negative. What we have is dy by dt is negative. So dx by dt is positive, x is increasing. So the movement here in the yellow highlighted area, x is increasing, dy by dt is negative, so y is going down. So the net flow is in this direction. So we see the net flow is in this direction. Now let's look at the other areas. I'm going to use different color for every area. So let's take this area now. Now in this gray highlighted portion, we are still above the y null cline. So the behavior of dy by dt will be very similar to what we saw before, which is that dy by dt will be less than 0. Now let's look at the behavior of dx by dt. Now we are below the x null cline. So remember, for dx by dt, we'll look at x null cline. We are below the x null cline, so which means that the value of y is less than what it needs to be for dx by dt to be equal to 0. So what we have is that dx by dt is going to be negative because y is less than what it needs to be for minus ax plus y to be 0. So here we see that dx by dt is also reducing. So if you look at the direction of the flow, x is moving in negative direction towards minus infinity because dx by dt is negative. Y is also reducing, so it's moving downward because dy by dt is negative. So the net movement will be in this direction. So here the movement is given like so. Okay, now let's look at another region. Let's look at this region. I'm shading it with light blue. The color is not important. I just want to make sure which region we are targeting. Okay, now in this region, we are below the y null cline, we are above the x null cline. Since we are above the x null cline, pretty clearly dx by dt will be positive. And since we are below the y null cline, what it means is that y is less than what it needs to be for the y null cline to be 0. since y is less than what it needs to be for y null cline to be 0, we know that derivative of y with respect to time will be positive. So x is increasing, y is increasing, net flow is in this direction. Now let's look at next region. This is a slightly warmer gray. Again, the color that is showing up on your screen is not important, but it's important that you know which area we're talking about. So I encourage you to try to solve this along with me, because that will help you understand what's happening here better. Okay, so in this warm gray region, we are below both x and y null cline. Now since we are below x null cline, it means y is less than what it needs to be for x null cline to be 0. So what it means is that dx by dt is going to be negative. So derivative of x with time is going to be less than 0. We are also below the y null cline, which means for y null cline, the y equation dy by dt, y is less than what it needs to be for y null cline to be 0. Y is less than what it needs to be for this system to be equal to 0, which means dy by dt is going to be positive. Because you see here, the y is a negative term. So what we are going to get is that y derivative is positive. So x is going down, x is reducing. In y direction, we are going up. So the flow is in this direction. Now, these are not very exact directions, right? There can be nuances. The angles might change, but this gives a general idea of how the flow is happening. Now, let's look at the gray area. Let's look at the one region left. So, this is a warmer gray, almost red. Let's look at what's happening in this region. In this region, we are below the x null cline, we are above the y null cline. Since we are below the x null cline, we already know how the dx by dt is going to be from here. We know that derivative of x will be less than 0. Since we are above the y null cline, we know that derivative of y will also be less than 0. So basically the flow is towards here. Okay, so now what we can do is we can look at the flow information we have, and we can, using the null clines, and we can already start getting an idea of the stability or the movement of trajectories around the fixed points. Again, this is like one of the first things we do. This is not definitive, but gives us an idea of what to expect, gives us a picture of what might be happening if a system is following a model that looks like this, or whose null cline phase portrait looks like this. Now let's look at what's happening in the neighborhood of each of the fixed points. So let's start with the third fixed point, which is here at the top. Now in this fixed point, notice that all the arrows are moving towards the fixed point, which gives me an idea that this is most likely a stable fixed point. You notice the arrows are moving towards the fixed point. The flow is never moving away from the fixed point. The angles might vary as the value, as the null cline moves up and down, the y null cline, depending upon dx by dt and dy by dt values, but it seems to be a stable fixed point. Now let's look at the second fixed point, which is in the middle. We notice that on the left and right of this fixed point, the flow is away from it. But we notice that here the movement is away from the fixed point. However, here the movement is towards the fixed point. So this seems like a good case for saddle node. Again, this is a rough understanding of what's happening here. Now let's look at the first fixed point, which is 0, 0. We see that in the immediate neighborhood, the flow is definitely towards this. So this is some kind of, there is some stability in this fixed point. So we are already getting an idea that the middle fixed point is a saddle with the stable manifold somewhere in this axis and unstable manifold somewhere along the x null cline, if not at x null cline. So even without finding the Jacobian, we already have an idea that definitely the third one looks like a stable fixed point, the second one like a saddle, and the first fixed point, which is 0, 0, has some level of stability to it. Now what we are going to do is we are going to go through our typical method, which is find the Jacobian, analyze the eigenvalues or the trace indeterminate, and for each of the fixed points, and then try to understand the stability of the fixed points. Now, the reason why we start with a rough estimate is, if this is not making sense for us, then we know we need to ditch the model and write a better model or a different model. But if this is making sense for the kind of system we are trying to model, we can proceed ahead with more complicated or more lengthy or laborious calculations. For example, that if you look at this system, if you look at this model right now, what it is telling us that when A is sufficiently low, there are three fixed points. The extreme fixed points, the smallest and the largest, are stable, and the middle fixed point looks like a saddle. So basically, depending upon the initial condition, so let me choose another color for here. So what it is telling me is that depending upon the initial conditions, so let's say we are starting to the left of the second fixed point, so somewhere here, then this both x and y will move towards 0, 0, which is a stable fixed point. If you are starting to the right of the saddle point, because see, notice the unstable manifold is in this direction too, which is pointing towards the other two fixed point. If you move to the right of the saddle, then the eventual fate would be the second fixed point, which looks like most probably it's going to be a stable fixed point. So right here, even without knowing the Jacobian, without knowing for sure the stability of the fixed points, I can tell that we're talking about a situation where if the initial values of x and y are below a certain number hinted by the stable manifold of the fixed point, second fixed point. So let's say if this is a saddle and this is the stable manifold of this second fixed point, and then this is the unstable manifold. Now again, this is a rough diagram. The unstable manifold does not have to coincide with x null cline, but it's very convenient in this diagram, so I'm going to stick with it. So depending upon the position of the initial values of x and y with respect to the stable manifold, the system will either end up in this fixed point, which seems to have some level of stability to it, or this third fixed point, which seems like definitely a stable fixed point. So what we're seeing here is that depending upon the initial level of x and y, which is the protein and mRNA, we might either end up having absolutely no relevant mRNA and protein, or we might have a certain high level, relatively higher and stable level of mRNA and protein. So even without finding out the characteristic equation, I already know that this system is telling me something about a switch. So depending on which direction I am with respect to the switch, I might end up with off situation where x and y are 0, or I might end up with an on situation where x and y have a certain value, a stable value. So it won't shoot up, it won't explode. So we won't have crazy amounts of protein, which is why self-limiting terms were very important. So since this makes sense, we are looking at expression of protein and transcription of the relevant mRNA. So this does make sense that we don't need a protein always, so we do need the off switch and we do need the on switch. So our idea of modeling a biochemical switch looks like this model could work for that idea. That is the only reason why we are going to proceed ahead and now find out the characteristic equation of this system and find out the stability of the fixed points for sure. Okay, so let's go ahead and do that. So this is our original biochemical switch model between the mRNA levels and the protein levels. And we are going to find the Jacobian now. So very simple for Jacobian, you have two equations, you'll have 2 by 2 matrix. Okay, so this is our Jacobian. We know that one fixed point is 0, 0. So Jacobian at 0, 0 turns out to be trace is minus a minus b, it's negative. So the trace being negative, which means we are in either third or fourth quadrant, and determinant is AB, which is positive. So we are dealing with the fourth quadrant. And then tau square minus 4 delta is a minus b whole square, which is going to be positive. So what we are dealing with at j00 is telling me that this 0 is a stable fixed point. So if we go back, there was some indication that this first fixed point might be a stable fixed point, and that is what our calculation using the Jacobian has told us, that j00 definitely looks like a stable fixed point. So we can update this system and say, yes, this is a stable fixed point, so we can color it in. And this is the off switch, and the red one is the on switch. Okay, now we want to find out the stability of the other two fixed points, the one that appears to be a saddle and then one appears to be a stable node. So for that, we have to first find out the other two fixed points, which can be very calculation intensive. So let's just spend some time looking at and analyzing our Jacobian. The trace here is always going to be minus a minus b, which is going to be less than 0. The determinant is ab minus 2x 1 plus x square, right? Very interesting. So depending on the sign and the value of our determinant, we will know whether we are on the y-axis, which is the axis for non-isolated fixed points, or we are on the third quadrant, which is for saddle node, or the fourth quadrant, which is for stable fixed points or stable spirals. Okay, so what we have here is del is equal to ab minus 2x by 1 plus x square whole square. Let's investigate the value of del and what changes it, what will make us a saddle point, because we already have suspicion that the second fixed point probably is a saddle and the third one is stable. So how do we decide which one is saddle, which one is stable? And all will boil down to the value of determinant delta. Now, one of the things I asked you to remember in the previous lecture was a very simple equation, ab 1 plus x square is equal to x. I called this equation number 2, that's the name we gave it. And I told you we'll be using this equation later on because I knew where we are headed. So let's say we put in the, I do not know what the fixed points look like right now. So let's just call x star and y star as our fixed points. So at our fixed point, tau remains unchanged because x and y do not show up in the equation for tau. The delta will be this, ab minus 2 x star 1 plus x star square whole square. Now remember, let's put x star here, so we get ab 1 plus square is equal to x star. So we can replace this x, we can substitute the value here. So what we get is determinant is equal to ab minus 2ab 1 plus fixed point square divided by 1 plus fixed point square whole square. So we can take ab out common. Determinant is equal to 1 minus 2 by square. Okay, so this is the system we get, and we can simplify it even further. Determinant is equal to ab okay, again this becomes very simple, and there is a reason why I'm doing this instead of directly finding the fixed points, because I know it's going to be very calculation intensive. Okay, now let's look at the system. What we ended up with simplifying is the determinant is equal to ab into numerator being fixed point x square minus 1 divided by 1 plus x square. ab is positive for sure. Denominator is going to be positive for sure for all real values of x. We are only talking about when we still have the 3 fixed points. This part of the numerator, which is x square minus 1, is going to vary with the values of x. Now, if x, the fixed point, is less than 1, if the fixed point is less than 1, then determinant is going to be negative. So if the situation we have is that if the fixed point is less than 1, for the x for the fixed point is less than 1, then determinant is going to be less than 0. We already know tau is less than 0. So what this is telling us is that in this case we'll have a saddle node, because now we'll be in the third quadrant of our diagram, a tau versus delta diagram. Now if our fixed point is greater than 1, then determinant is going to be positive, tau is going to be negative. So we are going to be in the stable portion, which is the fourth quadrant. So now we can either be a stable spiral or a stable fixed point, stable node. So for that, now we need to calculate tau square minus 4 delta to when fixed point is more than 1. So since we know we are going to have two fixed point, this is already telling us that the fixed point which is going to be less than 1, which is a smaller fixed point, it's going to be a saddle. The bigger fixed point is going to be stable something, a stable spiral or a stable node. So now what we need to do is find out tau square minus 4 delta. We already know that the smaller fixed point of these two, not the 0, 0, is going to be a saddle. That is for sure. The bigger one is going to be stable something. We don't know what the stable something looks like. Is it a stable node or it's going to be a stable spiral? That's what we are going to figure out by finding out the value of tau square minus 4 delta. If you remember, tau was equal to minus a minus b, and determinant we figured out was ab x square minus 1 by 1 plus x square. Here x, we are going to put it as fixed point, right? Because we are going to figure out what it is. Tau square minus 4 delta is equal to a plus b whole square. And there's a reason why I'm writing a plus b. And let me help you understand this very quickly. Minus a minus b whole square is going to be same as a plus b whole square. That's why. Minus 4 delta is going to be 4ab x square minus 1 x square plus 1. So here we are going to have a square plus b square plus 2ab minus 4ab into this is equal to tau square minus 4 delta. Now notice one thing very simply, that if this particular term x square minus 1 divided by x square plus 1 was equal to 1, if it was equal to 1, this rest of the equation will turn into a minus b whole square, which is still going to be positive, right? Tau square minus 4 delta is going to be positive. However, what we see is that this term will always be less than 1. X square minus 1 by x square plus 1 is always going to be less than 1 for obvious reasons. Sorry, not 0. This is always going to be the case. So what we notice is that under no circumstances is tau square minus 4 delta going to be less than 0, which tells me that the bigger fixed point is a stable fixed point. So this is always going to be less than 1, so we are going to have a square plus b square plus 2ab minus something that is going to be always less than 4ab. So this is always going to be more than a minus b whole square, which is a positive number. So what it tells me is tau square minus 4 delta is always going to be positive, which means that the third fixed point is always going to be a stable node. Now let's go back to our model. We have x here, we have y here. This is our x null cline, y is equal to ax. And then we have our y null cline, which looks like this. It's a sigmoidal curve. When a is sufficiently small, we have a stable fixed point here. We have a saddle here, and we have a stable fixed point here. So our suspicions were correct. This is doing a very good job modeling the biochemical switch. We also know that this is a situation where we have saddle node bifurcation. And one thing you would notice that the way we are treating this 2D system when it comes to bifurcation is no different than we did with 1D system. And that's the reason, because they're very similar. So now if you look at this, this is a saddle and these are attractors. So somewhere here, and I'm not drawing the exact value, but somewhere here would be one of the eigenvectors. Somewhere here could be the other eigenvector, the stable eigenvector. So this one could be the stable one, sorry, the unstable one. here we have a stable eigenvector. Let's say this is the stable eigenvector. So this is the stable manifold. And here is the confirmation of what we were discussing earlier, that if the initial point are south of the stable manifold, then all the trajectories will end up at 0, 0. Which means if our initial levels of mRNA and protein are to the south of the stable manifold, then both mRNA and protein will be removed from the cell. They will die out. They'll be removed. So there will be no expression of the protein. If the initial level of the protein and mRNA are to the north of the stable manifold, so I'll use a different color for this, then all the trajectories will go towards the stable fixed point, the third fixed point, which tells me that stable manifold is the basin boundary that determines whether the biochemical switch would be off or would be on. Of course, if the initial point is at the stable manifold, then the levels of mRNA and the protein, relevant protein, will finally reach the second fixed point. But any deviation, any aberration, any lessening or more going south or right of the values of mRNA and protein will end up with either the switch being turned on or the switch being turned off. Now the chances of the initial values of mRNA and protein to be on this stable manifold are very low. This is something we have discussed in past with Lotka-Volterra models. Alright students, this is all for today. In the next lecture, we will continue with 2D bifurcations. We are going to take a look at transcritical bifurcation in 2D, and we're going to use a very simple model. We are going to see how these bifurcations can be used for our environment forestry models, and we are going to look at the health of forest, which will be a continuation from the insect outbreak. But that's all for the next lecture. Thank you.